his PhD in mechatronics, robotics, and automation engineering. He's a recipient of the Presidential Fellowship by Carnegie Mellon University and the Conference Funding Award by the CMU Graduate Student Assembly. And he was also awarded second prize at the Bennett Conference for his poster presentation on robotics. Apart from this, he has more than 10 publications and more than 100 citations in renowned conferences in the field of robotics, in the areas of gripper design, miniature screw driving, and ball bots. He has also interned at ABB Robotics and Robosoft Systems. That said, I shall hand it over to our speaker for today to take it from here.
Hi everyone. Thanks Paramjeet for that introduction. Really quick, Paramjeet, you can see my screen?
No, it's blank. I'm not able to.
Okay. What about now? Did that work?
No, I can see you, but not your screen.
Yeah, it's working now, I think.
Okay, I guess. Yes.
Sorry for technical difficulties. We'll fix this in a minute. All right, how about now?
Yes, visible.
Awesome. All right. Hi everyone. Thank you for having me. This is a great initiative, and I think there's a lot that I would have learned from something like this. So today, I'll basically try and talk about what working as a researcher in robotics is like. It's mostly going to be my experience, but I'll try and cover all the things you can work on in robotics and eventually move on to some things that I have done. So let me first explain what I mean by full stack robotics. When I started as an undergrad in Manipal, that's me right here with hair, at Kapu Beach, I was pretty optimistic about things, and I wanted to become basically like Tony Stark, right? I wanted to be able to build a robot starting from scratch, be able to build his Iron Man interface, or maybe like Tadashi Hamada from Big Hero 6.
I'm sorry to interrupt, but the slide is still on the first. The presentation is still on the first slide for some reason. Oh yeah, it's working now. It's working now.
Yeah, this is horrible. Let me try again. There, better? All right, so I was in Manipal. This is when I had hair. And I basically wanted to become a full stack roboticist. I wanted to be able to do anything that is there that's possible to do in robotics. Okay. Eventually, I came to CMU, and I realized that's a lot of work. That's a lot of things to know, a lot of things to do. So can't be like these guys. But what does it really mean to work on the full stack of robotics? Why is it way too hard? And eventually we'll move on to the things that I actually focused on eventually. So whenever you talk about the full stack of robotics, firstly, everyone will say there's way too much to cover, but it all boils down to primarily these three areas: sensing, planning, and acting. You sense the world around you, you make a plan to do something, and you actuate your robot or act on the plan to modify the world. Okay. Now, eventually, you have to start thinking about more things. So you can't just run this sense, plan, act cycle again and again, because firstly, you need to design your system. You need to design your robot to actually do all of this. Sometimes that's in the feedback loop. Sometimes you're doing informed design where you do multiple prototypes and you design a robot. Uh, and also you learn a lot. So the robot can have systems in place that do the sense plan act, then change that cycle over time and learn new things. Okay, there's a lot going on though. So when you're designing the robot, you're thinking about how the mechanical design works, how electronics work, how firmware works, how the motors work, and so on. Right? What sensors you're going to put on there. Then when you actually are sensing the environment, there are things to worry about. There's state estimation. Where am I in the world? What does my state look like? And there are ways to do it. So you could do simultaneous localization and mapping, which is the first one. Computer vision are all ways to get your current state and the state of the world. Tactile sensing and force sensing, similar. The next stage is to plan. So given the current state of the world, how do I plan what to do next? Let's say I want to put dishes into a dishwasher. Should I open the door first? Should I load the dishes in first? Okay, we might think all of this is obvious, but in the world of a robot, all of this is extremely complicated. On a lower level, there's planning and optimization where you're trying to, now that you know the high level task of, oh, I need to open the door first and then put the dishes in. What does it mean to open the door? What should I do? Right? What my motor should look like, what my actuation should look like, and so on. And then once you have a plan, once you know what to do at like the lowest level of joint torques and joint positions, then you start thinking about, all right, well, I know where to go. How do I get there? Or if you're only working on, let's say, a robot that's a receptionist, what do I say? Right? So there's all of these things. And then what did I do wrong? Did I do something wrong? Can I make myself better by looking at what I just did? And that's the learning component of robotics, right? So there's a lot to compute here. There's a lot to learn, a lot to understand. But this is not really enough to cover the full space of robotics. Along with this axis of design, sense, plan, act, and learn, there is this whole other dimension to robotics. Where are you applying this full stack of robotics to? You could be talking about legged robots like Boston Dynamics does. You could be talking about manipulation and industrial robots. There's drones, there's UAVs, humanoids, field robotics, self-driving. There's a lot of stuff, right? So if you wanted to call yourself a full stack roboticist, you kind of want to check all of these boxes. And that's hard. Okay. Instead, today, let's only focus on a small subset of this full stack, which is how to make robots dynamic and reactive. Now, here's a cool video. I'll just start playing it and talk over it, but this is some stuff from the DARPA Robotics Challenge, which was set up kind of after the meltdown of the Japanese Fukushima reactors happened, where they were like, what if a situation happens like this? How do we send robots in to maybe shut off some valves, to navigate through rubble, find survivors, and so on? So here are some fails from that competition. And these are all really complex humanoids that were taking very deliberate steps. So if you actually looked at the competition, things were moving extremely slowly, except when they fell or when something went wrong, and then things would start snowballing and move really quickly. Okay. And I think the one after this one is my favorite one, where the robot is trying to apply a torque to the door to open it, but misses the door or the valve and just falls. Yeah, this one. Oh wait, no. Yeah, this one. Great. So here it missed the valve completely, okay? But it's still applying that torque, and that torque causes it to fall down, which is hilarious. Um, Now you could see something similar happen in real industry as well, um, but it's a little more subtle. So here, this is a robot demo of the robotic gripper trying to pick up a bunch of objects. Now you can see that every action that the robot makes is very deliberate, very calculated, and very slow. And this is not going to get us to the same level of human performance as quickly as we want. So what should we change, right? And I'm going to talk about here some examples that have actually tried to make robots a little more reactive. So this is the Minitar from Ghost Robotics. It's a tiny quadruped that basically has no gearboxes. So it's very nimble and very agile. And here you can see it jump up and open the door, which is great. Here's another example where they got rid of the gearbox, and you'll see a theme here. I will talk about direct drive a lot. Um, but here you can see this is a direct drive motor, and this arm is super reactive, right? It's trying to sense the human touch. Here it's an egg. The arm actually goes to this point, but when they put the egg in there, it'll figure out that there's something stopping it and stop. Right? So the forces applied, the impulses applied are a lot lower. Okay, awesome. So people are working on this. And well, so have I been working on this. And I will talk about 3 areas where we can see a clear picture of what it means to make robots more dynamic and reactive. The first I will talk about is the ball-bot. The ball-bot is a single-wheeled robot that balances on the ball. And then I will talk about reactive manipulation and how we can make robot grippers, a lot faster, a lot more agile. And then I will talk about the contact localization method, uh, which is extremely simple, and it kind of helps us get more information about the world. Okay, so there's a little bit of design, a little bit of actuation, a little bit of sensing, if that's a good classification for things. All right, starting with the ball bots. Here's a robot called the PR2. It's a very advanced robot. It was built a long time ago by the guys that made ROS. If you're familiar with ROS, you will know. But let's look at the design of this robot. So the first thing I notice is this giant box at the bottom. Why does there have to be this giant box? And this is the base. So this is where all the motors are for moving the robots, because it's a mobile manipulator and it has to move. Now, the reason that this giant box is there is because, let's say we wanted this robot to go up a small slope. When the center of mass of this robot is not within this box, it'll tip over. So the smaller the box, the easier it is for the robot to tip over. But if you look at the ball bot, the width of the ball bot is about the same as human. So what's happening? Why does this work? The reason is that the ball bot is kind of in the business of falling over. Okay, it's constantly falling over. It's just that when it tries to fall over, the ball at the bottom catches up. And we see this happen when we are walking as well. When humans walk, when we take a step forward, we move our center of mass so that it's in front of us, and then our legs catch us. So the leg that's walking in front of the other is going to catch you from falling. And that's how walking happens. So it's the same idea, except now here it's continuous. Okay, so the ball bot leans forward and the ball catches up. And if you do this fast enough, you can get the ball bot to kind of stay in place. If you're familiar with this idea of balancing a hammer or a broom on your fingertips, it's more or less the same idea. You're trying to move your hand fast enough. So while the head of the hammer or the head of the broom falls slowly. All right, great. So this works. This worked in 2006. Now, how did it work? There was this whole idea of the inverse mouse ball drive. And if you're familiar with mice before optical mice existed, it was basically this system but inverted. So you would have a ball inside your mouse, and you would move the ball around on the surface, and the ball would turn a bunch of rollers, and sense the roller's position will be sensed and converted into mouse movements. Here we're doing the complete opposite. You're actuating the rollers to move the ball. And here there's the motor, there's a belt drive, and these rollers squeeze the ball in and actuate it in the particular direction we want it to move. Okay, so this all worked great. This has been working great for more than 20 years now. But there were some problems. So the first problem is that because there are so many moving parts, there's a lot of friction, there's a lot of backlash. These belts would start failing. You can see some of the fraying right here in this picture. Then because when the ball was moving in one direction, the rollers were perpendicular to it. So those rollers would actually slip and cause a lot of friction. So there were these two big problems that I tried to address as part of my master's work. And the solution was to make the ball bot with the minimum number of moving parts. So you had to do something where you would take all of these complicated moving parts and move them into software. How does that work? Right? What is the minimum number of moving parts for a robot like the ball bot? It's two, right? That all you need is a ball and all you need is a body. If you had a ball and a body and you had a way to actuate the ball directly, you could build a ball bot. So how do we actuate the ball directly? We use something called a spherical induction motor, which was basically designed and built by the Microdynamic Systems Lab. And the idea is, instead of having one rotary axis in your motor, you have three. So this ball can be actuated to move in roll, pitch, or yaw. How did this work? There were these 6 stators at a particular configuration that was decided by some math. And we said, all right, whenever we move one of these 6 stators, the ball will rotate in that axis. So we can come up with some maths that tells us which direction to apply forces with all of these stators to move the ball in the desired direction. And just to sense where the ball was, we now switched over to another technology that was first pioneered in computer mice, which was these optical laser sensors that would track surface scratches on the ball to tell us where the ball was. Now, here's what the operation of the ball looks like. This is in pitch. There's going to be a roll axis. And this is the yaw axis. Great. Now we can move on to putting one of these things at the bottom of a ball bot, right? It took about a year with some serious PID tuning and engineering, but we were able to get this working. And here is the ball bot lifting off and starting to balance. And now it's just balancing on that one ball. There are no more moving parts except these balls. And there are some moving parts in the legs. But here's a young me trying to push the ball board around. And see, what's happening is, as soon as I apply a force, the ball board starts falling and the ball starts to catch up. Uh, Imagine this as basically a two-dimensional Segway. Here the robot is station keeping. So we told the robot to not move from its point on space. And all it was using was the sensors in the ball to figure out where it is in space. Okay, so there's some state estimation involved here. I think one of the hardest parts of this project was to get the winding of these motors done, because we had to do all of it in-house. And here's a lesson that you would normally not know about when you start working on hardware in robotics. Most of the time, you have to build your own stuff. You cannot just buy most of these things off the shelf. And it ends up being a lot of work. So yeah. So if you can work on software, because we have a saying that hardware will add 1 year to your PhD. So try not to touch hardware. Although try to touch hardware, because we want people who work on hardware. We need to improve the state of robotics hardware. Awesome. Now let's move on to this idea of the ball board and being direct drive, which means there were no gearboxes, no transmission elements. And try and apply this to how robot hands work. So when I started my PhD, I started in the manipulation lab. And here I was basically thinking of this question of what hands are for and how we can make robot hands more reactive to contact. Now, one of the things that I noticed was current robot hands are all built like a vice. So they're built to squeeze stuff really strongly. And for that, they're very strong, they're stiff, and they're very resistant to large disturbances. So if I pulled on the fingertips, they wouldn't really move. But compare this to an actual video of Julia Child. This is Julia Child from the cooking show. She's trying to cut a potato, and see how nimble and agile these fingers are. Right? Also, notice that they're never actually grasping anything really. It's all surface contact, and it's all just the hand bracing against environments. So what human hands are actually doing, and this is what I think hands are for, is to support a wide range of interactions. And for that, we need like a lot of different ranges of stiffnesses. We need a lot of disturbances that will be applied to the hand, and we need to be able to react to them instead of just absorb them in the structure. One of the main distinctions we saw here was that robots at this point tend to avoid contacts. And this is something that I think needs to improve. While human hands, we react to contacts and we kind of embrace them. We know that we're going to make contact and we're okay with it. Now, the trick to make robot hands a lot more interactive is to get rid of this thing, the gearbox. A gearbox is great when you want a strong, stiff robot, because it improves the torque that you can apply to the world. It makes the motor move faster and hence more efficiently. And a gearbox will basically reduce your speed so that you're moving slowly. But when you want to make agile, reactive decisions in the world, this is bad. Because one, you've reduced your speed. You can't move fast enough. You also increased your inertia, because when you look at the inertia of the output of a gearbox, it gets multiplied by this n squared term. Okay, that's bad. Above that, we also have friction and backlash as losses, which is also bad. We don't want a loss in our drivetrain. So instead, we decided we will build a direct drive gripper where the motors were directly connected to this linkage. Now there are 4 motors here, and right, this is a better picture. So there are 4 motors here and here, and they all control this 5-bar linkage. And the cool part was, if I apply a force here, the fingertip would give. Okay, it was extremely backdrivable. So any forces applied at the end effector can backdrive the joints. I'll not talk about the rest of the stuff here because if you have any questions about this, we can talk about it later. But all right, so this is the DD hand. This is a direct drive hand, and it's extremely nimble. You can do a lot of cool things with it. Here's the, it actually jumps. Yeah, that's basically the speed at which we operate the gripper. Great. Now, so what do we do with this gripper? Now I remember I showed you this video of the robotic gripper trying to pick up parts. This is how the robot would do it in industry. This is about the speed you would see in a normal industrial work cell. Here's a slow motion video of how a human does it. So you'll notice that first the fingers actually make contact with the ground right here, and they start grasping the object, and then they pick it up really quickly. Right? This is quite a big improvement over what we saw the robot do, right? And that's because human hands are extremely efficient. So now the question is, oh, and I call this the smack and snatch behavior because you basically smack your fingers into the table and snatch the object away. But now, can we do this with robots? What would it look like if we tried to do this with robots with a highly reactive gripper? Now here you would see that the robot moves down. This robot is actually extremely stiff. So this robot is just a normal industrial robot that will try and pick up this block. The first thing it will do is move the fingers towards the surface. As soon as the fingers detect contact with the surface, they will start picking up the object, and the hand will start decelerating and then accelerating upwards. So that's what it looks like in 1 second. But in slow motion, this is exactly where the fingers meet contact. And at this point, the robot is still moving down. So it's still moving down. At this point, the robot realizes I need to stop and starts moving up. And the inertia is so high that it takes a while for the robot to decelerate and then accelerate again. So let's look at it again. The robot, the fingers make contact, the object is grasped, and the robot moves back up. If you look at how long this action actually took, the grasping takes about 10 milliseconds, which is amazing. And the whole action takes about 1 second, which is almost an order of magnitude faster than what we saw with the robotic gripper. So we're kind of moving away from those deliberative actions to more reactive actions, and we get a performance benefit. The next question we should answer is, well, if we want to be reactive, we should know where our contacts are. How do we figure out where a contact is on a link? There are a bunch of ways to do it. So normally you could do it with vision. You could say, I have a camera looking at my object. I have a camera looking at my finger. I will just try and find where the contact is. Or you could put sensors on the finger. You could put touch sensors in the finger. But we'll go one level a little more crazy. We'll say we will put no other sensors except what we already have on our robot. And most robots already have joint sensors. So they already have encoders at the joints. They have torque sensors sometimes. So how do we do this with no other information except joint sensors? Now, the problem we're trying to solve is we have a robot link, which is some abstract body. We have an obstacle, which is another abstract body. And these two are in collision, and we need to find this contact point. Here's the simple graphical representation of this method. Now, this link comes in contact with this obstacle right here. After this link is in contact, there is this thing called a center of rotation. So every body in space can be represented by a translation and a rotation, or just a pure rotation. So you could find a point, even if it's a translation, you could find a point in space which when rotated by a particular angle, you will get the same motion. So that's called the center of rotation. And let's say this is the center of rotation of this body. What I'm going to do is I'm going to draw a bunch of lines out to the surface of this body. And I'm going to mark two things. I'm going to mark the normal direction at this point of the surface. So that's the normal for each of these points. And I'm going to mark a velocity direction. So the velocity direction will be perpendicular to this ray that we cast out from the center of rotation. Now, the method is really simple. You basically take all those points that you just mapped out, and you see if the velocity is perpendicular to the normal. If the velocity is perpendicular to the normal, you mark that as a contact point. Okay, and then now we have these two options. This is where the velocity is normal. This is where the velocity is normal. Now, we just filter out these velocity points, these candidate points, by looking at the velocity before impact and seeing if it fit in the bill. Okay, if the velocity was along the normal, so if you were moving this way, then we could have made contact here. If you were moving this way, then we would not have made contact here. So this is probably a candidate and not this. All right, why does this work? Because let's say there's an obstacle here. If you had a non-zero velocity in this direction, that would mean that this object was inside this obstacle at some point in the future, which is bad, which cannot happen. And therefore, this is a valid strategy. Okay, so now we can run this on our DD hand. All we have is information of the joint torques, and this is the linkage plotted over the camera video. And notice that the hand is moving actually quite quickly. This is 1/16 speed. And you'll see a point here that's going to mark the location of contact for the linkage. And okay, so we could also do this with more complicated mini towers, which is a different linkage here. And all I'm going to say about this, you don't have to read this plot, but all I'm going to say is it works pretty well. And we can detect up to within a centimeter of where this contact location point is. Awesome. So overall, today I've talked about these three areas where I've tried to make robots more dynamic and more reactive. The first is the ball bot. The second is a direct drive hand. And the third is how we can sense contacts and make robots more dynamic. But how does it relate to my goal of becoming a full stack roboticist? Because that's where I started, right? And it's pretty bleak. I haven't really checked a bunch of these boxes, and there's a lot to go. So this will kind of make me wonder whether the goal of becoming a full stack roboticist at this point is achievable, but I will keep trying. And at this point, I'm going to stop giving my presentation. and acknowledge all my collaborators. Matt Mason and Aaron Johnson are my PhD advisors, and Ralph Wallace was my master's advisor. Most of this work was done in two labs, the Microdynamic Systems Lab that's headed by Ralph Wallace and the Manipulation Lab that's headed by Matt Mason. Most of the funding for this work has come from the National Science Foundation in the US, and it's a great sponsor. So if you get a chance to work on an NSF funded project, that's the best thing you can get in the US. At this point, I'm going to end my slideshow and take questions, because I think it's going to be a lot more interesting to see what you have to say than what I have to say.
Yeah. So thank you so much for that amazing talk. There was something in there for those just starting out with robotics, as well as those of us who know a little bit about it. It was beautiful how you covered the basics and yet delved so deep into the topic. Now let's get to the questions. The first one that we had in the chat was, how did you go about choosing the topic? Like, did a mentor give you the topic, or did you?
Okay, so this topic of there are multiple topics we are talking about here. The first topic is the broadest one, which is how did I choose to do robotics? That's the easy answer. I think Professor Vitleshwar tried to convince me to take mechatronics at some point, and I caved, and that kind of started that whole process off. For the second level, which is dynamic and reactive robots, that topic shows up in hindsight. Right? You never walk into doing research thinking I will work on dynamic and reactive robots. Right? You think about what you have worked on, and you say, "Oh, this kind of makes my theme look good. Like this fits the bill." So I'm going to say I work on this, and this is in hindsight. The third is at the individual project level, and it depends on what stage of research you're in. So right now, if I choose to work on a project, I will pick my own project. And if my advisor tries to convince me otherwise, I have the right to say no, I will still work on the same thing that I want to work on. But that's at the tail end of your academic work, right? When you start trying to get out of PhD. Before that, it's a lot of shopping around. So you go to all the people and you're like, hey, do you have a cool project I could work on? And they give you an answer saying, yes, I have a project, here's what it is. And then you're like, that's not cool enough. I'll go try something else. So that's basically how you pick projects. You just think of things that you think are cool. Make sure that no one's done them before, and go for it. So yeah, so research is basically recce for cool things, and then a literature review saying, all right, I'm sure no one's done this before, it's worthwhile to pursue this.
All right. So the next one is, why did you choose robotics hardware? Because most of us would just pick the easiest thing in sight and just work with software and simulations.
I'm going to go back to the same answer I gave earlier. You pick something cool, make sure no one's done it before, and you work on that. Hardware is a lot harder to work on. It's more complicated. There's a lot more engineering hours that you need to put in, but it is also the most rewarding. The example I like to compare this with is, if I were to sit and train a neural network on ImageNet, it's not as rewarding as trying to build something physical. That's personal. That's my opinion. I'm sure there's a lot of other people who think otherwise. So yeah, my personal opinion is I like to see things move, and that can only happen when you're looking at robotic hardware. It is also more, it's also easier to do something people haven't done before. Um, Kind of makes it easier to pick a problem, and you don't have archive anxiety. I don't know if you guys are familiar with this term, but there's this new thing called archive, where you will see a lot of people post their papers before they actually publish them. Okay. Hmm. So you want to. So every morning, I know people who wake up every morning and they check on archive to see if they've been scooped, because there's always someone else working on the same problem, and if they get to the solution before you, then whatever you spent doing is probably not as worthwhile as it was the day before, right? So this archive anxiety doesn't exist in robotic hardware.
What sort of frameworks do you work with? Like now, the only thing we hear about is ROS. What do you think is the importance of that? Is that the framework that you use for everything, or is it just new at the moment?
I like ROS. It's easy to use. It's pretty much standard in most robotics research. But as soon as you go into industry, the shortcomings of ROS start showing up very quickly. It's not really a tried and tested system, so um, you can't deploy it in industry. It's going to break really hard. So eventually, what everyone does is write their own DDS, which is a distributed message delivery system, which is what ROS also works on. But everyone writes their own, and eventually, in industry, ROS is never used. But the barrier to entry for a student or a researcher is so low that that's what is favored in academia.
Speaking about industry, what's your opinion on the gap that exists between the research side of robotics and the commercialized side of it?
Um, this answer has changed over the 8 or 9 years I've been doing this. So the answer, if you asked me when I started working, was there's more money in academia because there were not a lot of companies working on robotic solutions. But things have pivoted so much over the last 10 years that currently it is beneficial if you're in industry because there is a lot of money to work on things, and any sort of research costs a lot of money, right? So, so there is a lot of money. There's a lot of funding. There is a lot of infrastructure that's not available in academia anymore. That's there in industry. The only thing that's the other side of the coin there is the freedom. So the difference is in academia, you can work on whatever you want to work on. In industry, you work on the problems the company is facing. So these are the basic distinctions. But now we are seeing places like Microsoft and Amazon and Apple are all starting to publish papers. So you can actually go work on things that you want to work on in industry as well. So that's also pivoting a little bit. Especially with all of these companies like OpenAI and NVIDIA all starting up these giant research houses. They're basically operating like academics inside industry. So you have access to the same money, same funding in industry, and you have the freedom to do whatever you want.
Okay, these next questions are more of life advice type.
Yeah.
So we are all currently at home and we are on an online semester. We don't have access to hardware per se. So,
Yeah.
it's largely evolved. The questions are largely surrounding the theme of, first of all, it's Carnegie Mellon. If you're from Carnegie Mellon, how it's like the most prestigious for robotics. How would we get there? Like, we don't have any experience. We can't get any hardware-based experience kind of online. And that's like the generic theme of the next question. Like, what skills do we learn while being at home, or what sort of projects do we do given everything's online?
That's an interesting question because that answer has changed as well from when I started. Because I got to CMU as a bunch of lucky incidents. Okay. I think I was at the same place. I had very minimal experience with robotics. In Manipal, all I had done was one of those tech tatva competitions for robotics. And basically all I did was try and keep a good score, and I was just curious about all of the tech in robotics. But yeah, that was basically it. Today, although, if you want to get into a robotics program in the US, you guys are so quick with publishing papers in computer vision and in all of these software related things that if you don't have publications before you come here, you will probably not get admission. Like especially a place like RI, where mostly everyone entering the university at this point almost has one or two publications on their belt. So here's what I think you should do is to find problems that people haven't solved and write papers about it. Paper writing, I don't like this. You should not have to do this to get into a research program, but that's what the situation is. So yeah, try and figure out faculty to work with, try and get internships at different schools. The more schools you visit or the more schools you spend time at, the more breadth you have of experience, which is well accounted for. But in terms of doing projects, just do whatever you think is cool. Like go learn OpenCV or do some projects in OpenCV, do some projects in TensorFlow or something, which you can do at home. Yeah, you don't really need access to hardware to get started in robotics. Simulation tools are really improved. So go download ROS, open up a robot in Gazebo, play around with it. Not as fun as hardware, but doable.
All right, so some of the audience who is a little more well versed with robotics wants specific skill sets. If you have any advice as to any certain skill sets that you should be learning.
If you're not a computer scientist, learn algorithms. Okay, it's going to help you all your life. Learn how to write code. That's the first step. Because everything starts from code. And if you can write good, efficient code, you're going to be at a step higher than everyone else.
And that is advice you stand by even after having worked solely with hardware, largely with hardware.
Oh yeah, do you not think I write software all day? I don't really like the hardware design part of it is like maybe 2 months, and then you're just writing software. It's all about software at this point. Every field has transitioned into being a software-defined field. Be it mechanical engineering. So at this point, mechanical engineering is all about writing MATLAB code and simulations. There's really not much mechanical engineering you can do now. Okay, it's all been figured out. So yeah, most fields in academia have switched over to using software tools extensively.
All right. So there was actually a question that I kind of put in there, but the question was that it's by a person in Ramya wants to know that they're a CS student and they don't have any knowledge on hardware and mechanics of robots, just have a vague knowledge, but is proficient with ROS and simulation software.
Okay.
So they want to know how to enter in the whole area of hardware, or what could be the next steps.
The next steps. I like the idea of working on the simplest robot, which would be a line follower. Right, that's where I started. That's good enough. That's an entry point. But eventually, what you could do is you could buy one of these. Like I like Mindstorm a lot. You can do a lot of quick prototyping with the Lego Mindstorm kits. Uh, those are great. There's a lot of these Lego Technic stuff that's also available. So if you want to get quick into hardware, sorry?
Did you get those in India?
Mindstorm and Technic, I'm sure you do. They're expensive, but you do get them. But you could also go to your shop, buy an adapter that gives you 12 volts, buy these really cheap. Now you can buy microcontrollers for really cheap, like a 600 megahertz TNC is like $20 here, which is what, 1,000 rupees in India. Go buy a microcontroller, try writing some firmware, because the mechanical design aspect of things is not that hard, and you should be able to pick that up really quickly. Well, making non-optimized designs not that hard. But I think picking up firmware is complicated. So that's a skill that I wish I had better knowledge about. How to write good microcontroller firmware.
What sort of microcontrollers do you work with?
I keep switching, so it depends on what task I'm doing. So for example, all of the firmware that was written for the SimBot was written on a PIC microcontroller, a DSP, and that was just because somebody else had done a little bit of the work before I came. So I had to learn the DSP language for PICs. For the direct drive hand, I wrote all of my code on Texas Instruments chip, which at that point was something that I thought was easy to do and had the most support for. So most of the time, I'm just looking for new microcontrollers and see if there's enough support for it, and things will be easier to deploy or not. And if I think I like a particular toolchain, I will go with that. That's my idea. But mostly it's all very similar. Once you understand the lower level working of things, it's all basically register access, and so you can just quickly switch between things. But Arduinos are great. I don't use Arduinos as much, but Arduinos are great, and they're more than enough for doing things at undergrad.
Why not? Why do you not work with them? Is there a reason, or is it just the people before you worked with something and you just followed suit?
Yeah, I haven't yet bought into the Arduino craze. I'm more old school than that. Yeah, mostly I don't even write C++ code in firmware. It's all C code, and it's all fixed point math, which is interesting. So if you're interested in firmware, fixed point math is something you should know how to do. So if I were to explain it really quickly, it's basically trying to represent a floating point number in integers. So basically you can choose where in that integer number your decimal ends up. And if you do not have a floating point capable microcontroller, knowing how to do fixed point math is going to save a lot of trouble for you, because then you can write fast and optimized code. But if you're trying to get into hardware and firmware, fixed point math is one of the things to know.
Okay, the next set of questions are CMU specific. One was, is the only way to work with CMU professors at an undergraduate level through their RIS program? Or
Yes and no. I think the official answer is yes. Everyone recommends that you go through the RIS program, although you might get lucky if you email someone and they like you. So, yeah.
considering we are all at the stage where we are trying to reach out to professors, do you have any advice on how to be more quote unquote likable to them?
So I know some people have filters and they will kind of ignore emails coming from Gmail unless they know you. So mostly because you get so many emails from Indian students that they have these filters in place that kind of figure out if you've emailed them, and they will put them in a folder and never worry about them. Okay, so you will never even get to their eyes. Some other people read all their emails and they're awesome, and they will go through everything. If your email looks like a blanket forward, it's probably going into the delete box. So yeah, write a personal email, ask them questions, because if you don't ask them questions, they have no reasons to reply, and know about their work. Don't email every professor in a university saying, hi, I want to do an internship with you, because then you know, because people talk. Like every time I get an email from someone nondescript who I've never seen before, um, I'm pretty sure a lot of other people get the same email. And one time I replied to this email, but one time I got an email that looked like it was a mail merge. Uh, Somebody had written a script to find every email address on the RI page and kind of sent everyone a personalized email, and that was pretty cool. But that's a one-off. So I don't think a lot of people thought it was cool. I just thought it was cool because I kind of figured out there was some Python magic going on in the backend. But yeah, we all talk about emails. So write a good email, write it well structured, ask questions, ask pertinent questions. Yeah, that's all I have to say.
Just out of curiosity, did the Python guy get a reply?
I replied. I also showed everyone that I thought that it was a scripted email. And it was really cool trying to compare these emails. But again, I don't think you will end up being able to come on an internship or something this way. I think you either want a professor who knows someone there and has a connection, or you want a stellar resume to be attached to that email.
All right. The other stuff was, what are the projects like at Carnegie Mellon? Does Carnegie Mellon do things in medical robotics, or is it mainly focused on self-driving cars?
I think we cover everything there is to cover in robotics. So there is, if you're interested in medical robotics, there's someone working in medical robotics. You have space, there is field robotics, agricultural, anything you can think about, we're probably doing it. It's a team of 1,000 people that are working only on robotics. So it's pretty great. But yeah, The best place to look, obviously, is the RI webpage. There's a whole list of projects. Um, I actually don't know how often that's updated, but it's a good reflection of what the breadth of the place is. And there's a bunch of other places. So Oregon State has a great robotics program. WPI has a great robotics program. Georgia Tech, until recently had, I don't know if they still do, but Georgia Tech is great. Um, Northeastern or Northwestern, they're all good places to look at.
Okay. This is a question. Not okay. Okay. When we are looking for robot institutes, do we look at the university or do we first give preference to the labs more than the university?
I think if you're doing a master's, then a university makes more sense. Because master's work is mostly 50-50 split between research and coursework. So make sure you like the coursework, you want to take the classes there, because if you don't like the coursework, there's no point in going to do a master's. Places like RI are a little different, where the coursework requirement isn't as strong and you spend most of your time doing research, where they ask you what areas you kind of want to work at and see if you have openings available. But for masters, university is more important, I would say, unless you specifically have a strong tendency and you kind of want to work with this professor, you think he's great, his work is great, it makes sense to go by lab. Um, but I think you will get the same level of knowledge from the Oregon State program as you would from the CMU program in terms of coursework. For research, it's a slightly different story. Well, is it? It's not really.
All right. There's one which was again life advice. How tough would it be? Would the journey be if one were planning to do an STE role in a year for a year or two in a company before looking into masters in robotics?
Hey, that's what I did.
Right.
I was working at Mahindra for almost 2 years before I decided I did not want to do a desk job in India and I wanted to study robotics. So, yeah, it's totally doable.
So,
I don't think things change. I think you get more experience on a job anyway.
so what did your resume look like? I mean, if you don't mind answering, when
resume.
you applied for the first time for masters.
So I had my thesis project where I built a self-balancing robot, but that's all I had pertaining to robotics. Um, I had I had an okay GPA. Um, I had a good GRE score, but that's all. Um, I think it's also a little bit about what your resume is not as important when you're an Indian undergrad. I think they'll look at your college and they'll be like, all right, you passed the bar if you're from one of these top 20 schools or something. Um, but I think mostly they look at your letters of recommendation. So if you have some strong like letters of recommendation, you should. That's what you need. And now you need publications, but that's a different story.
All right. I guess don't have a lot of more questions. Let's just have this last one. This was what sort of projects would you advise for someone just starting out right now to be eligible for applying to RIS or in fact even Carnegie Mellon later on for masters? Like what sort of project? Given it's online.
Given it's online, oh, that's a harder question. Uh, Something that demonstrates your foundation in math, something that demonstrates your software skills. Those are the two main things that you should look at. Do something that has some component of uh, linear algebra or math required. Um, but I don't think I can come up with a project because it's really hard um, to do stuff like this while you're at home, remote, not working with people. But if you can, oh yeah, there's some great stuff. So see if you can find some simulation challenges. So very recently, the DARPA Subti challenge was available as a simulator challenge. And these are more investment. So you're kind of invested in that project for 6 months to a year, but you can do a lot of work if you focus yourself and not do lots of small projects, but instead just pick uh, the DARPA Subti challenge or whatever is happening at that time. Uh, there is always a simulation component that you can do using only your computers at home. Um, you might not get very far, but the fact that you put in the effort is valuable.
So, in your opinion, should we as students be doing multiple smaller projects in slightly different areas, or just one big project in one specific area?
Both are valid. You can choose either which way you want to go. Most of the time, you end up writing a statement, right, for this and for other programs. You basically have to do a good job at talking about what you want to do and demonstrate that you have enough knowledge that you can achieve that goal. So yeah, find out what's current research and see what's missing. If you can just identify that and write about it in your statement, that will give us a good idea that you've done your homework. Right? And it's mostly PhD students that end up receiving the RIS applications. So there's it's a good mix of PhD students and faculty. So we all know what's happening.
Interesting. So, do you have any insider tips for us?
No,
Further?
CMU is extremely structured. Unfortunately, there are no tricks. Um, there is every year there's a PhD admission committee, there's a master's admission committee, there's a risk admissions committee, and there's 6 people who you don't know who they are, and they're all only those guys read your uh, applications and say yes or no. So it's a very secretive process, and there is absolutely no pull any faculty or student can pull. There's no effect you can have on that decision. You just find out if you got in or not.
All right.
So this at CMU RI it's very different because it's all committee based, and so it's similar at MIT, it's similar at Stanford, but some other places are a little different. So Oregon State is a little different, where all the professors read all of the applications, and they pick and choose who they want. So you need to get a admission letter from the lab and the professor and faculty. So each place has its own system that works.
Got it. Actually, this one's a continuation for the previous question, the big versus multiple small. Would it be more helpful if you have a complete hardware prototype that can be directly applied in industry, or will it be more helpful if you have 2, 3 papers that are accepted in conferences for a master's application?
That keeps changing depending on who's reviewing the thing, but I think I would say both are equivalent. If I was on the committee, I would say, hey, cool, there is actually working hardware stuff versus a couple of software papers. I would value them similarly, but you don't know who's reviewing your application and what they think about you.
Very well.
Maybe it's a super strong academically minded person, and they're like, well, who cares if they build something? Like, where are the papers to show for it? So, but yeah, especially at CMU, you're competing with a lot of um, amazing people. So, like, anything that helps you stand out is good.
All right, I guess that's it for the questions. Stephen would like to say a few words. I'll hand it over to him now.
Yep. First of all, thank you, Paramjeet, and thanks a lot, Ankit. Like your presentation was very interesting, and especially the videos that you used with the ball bot. It was very cool to look at, and it was great having you here. And hopefully, in the future, we would be able to interact again if you're up for it. And the question answer session was very insightful, and we still have like a lot of questions left, but we just don't have the time right now. So for that, like if guys, if the audience, if you have any more questions, you can approach RSM. We'll try to get your questions answered. And yeah, just it was great having you here. Thanks a lot.
Yeah, this was fun.
All right, so before we leave, the event is done, and I would like to say a few things about RSM. So RSM is an research society Manipal. It's an organization that it was started to kind of promote the idea of research among undergraduates, and we actually host a lot of events, not just this one. Like this was Cognizance, which was kind of in the spirit of RSM to kind of promote the interaction of students and promote research in general. We also host like alumni webinars, paper discussions, and a lot of other things. And you can stay up to date with that through our Instagram page and our LinkedIn page. And we also have a lot of projects that you can, if you are interested in joining, you can join it and collaborate uh, with professors and other students. And these can be, you can look at these on our website, which we'll put on the chat. And yeah, there's also a suggestion box on the website. So in case you have any suggestions or feedback, uh, you're welcome to put it. And yeah, thank you everyone. Thanks for joining. And yeah, special thanks to the guest, obviously. So yeah, with that, the event is done. You guys can leave.